And this is basically using the terminology we've been developing yesterday. It's really logical equivalence for polymorphic types. That's if you want to situate it in the setting that we've been developing, that's what we want to do. We want to talk about logical equivalence. So we had a number of motivations for it, which Dan gave you this morning. But the main idea about the whole thing is that the idea of polymorphism, which informally has some idea of uniformity or genericity or something or other about it, can be exploited so that we get notions of equivalence of things of polymorphic type, which has the characteristic that it cuts down very greatly the number of modulo observational equivalence. It cuts down very greatly the possible programs of a given type. And so this is the phenomenon that gives rise. This is what gives rise to the phenomenon that if you've had experience in programming in a decent programming language like ML or Haskell, then you have the experience and you know the experience that if you write the code and it's type correct, it works. Okay, and there's a theory that's behind that. It's not just like our little cult and that's what we believe in. There's actual math behind it. Okay, so that's what I want to talk about. Okay, so this is what we're going to do. So the thing we talked about. So the thing we set up. Let me recap a little bit the things that we were doing last time, so I can put them all in a proper perspective. So last time Dan and I did two things. So last time we set up two things. One very sketchily and one is more fully developed. And now I will explain to you the reason why we did it in that way. So the one thing we did in the morning lecture yesterday is we developed this idea through an attempt at proving termination of what I called hereditary termination. Okay, at type tau. And we can define this by induction on the structure of tau. So the idea was that we're looking for a theorem. I'll put it over here. So our first attempt was we were looking at a theorem, and I'll weaken the theorem because it suits my purposes for this lecture. We were looking for a theorem that said, at the very least, if I have a closed expression of natural number type, then there has to be a value necessarily of that type such that it goes to that value. And this I'll just write as E converges, okay, written like that. So this is what we were going for. And then in the process of trying to prove this, we developed this idea of hereditary termination. So here's a variation on what we actually did because it helps me connect with what we're going to do in the rest of this lecture. So we defined what to do at natural numbers, and we define this as the strongest predicate satisfying these conditions. Either it evaluates to 0, or it evaluates to the successor such that the successor is itself hereditarily terminating at type net. Okay, so that was clause number 1. Clause number 2, in this sort of revised form, which is suitable for that theorem, is to say, well, at function types, I don't care about anything about what the function actually is or anything. I could give a damn about that. This is an important insight. All I care is how it behaves. So it says if you give me a hereditarily terminating argument of the domain type and I apply it, then I get a hereditarily terminating result, a result of the codomain type written like that. So this is important, okay? So a few things to observe is that about both of these we'll mention. Nat is an inductively defined type, and hereditarily termination is inductively defined. Function spaces are defined via a connection to logic. I could sort of write this as like an arrow, but the arrow would mean logical implication. So the idea is that this is implication. Okay? So the idea is that we're giving. So the important point here is that what it is, the important thing that we're exploiting here is that types induce behavioral specifications. Okay, that's the important point. Because what I'm doing here is I'm saying if I know the type of an expression, here a closed expression, and I know its type is a function, what I know is it's the sort of thing that sends, arguments that behave like tau 1 to results that behave like tau 2. This is what is important, okay? So that's what we're doing. So the critical thing is that. Now the interesting thing is I'm going to exploit a similar mode of reasoning in a moment, so I'll bring it up now, which is, you'll notice, as I just remarked a moment ago, the definition couldn't care less what E actually is, okay, in this formulation. I know last time for other reasons I did something else, but okay, it doesn't care that it's actually a lambda. The only thing you care about is it obeys the call and return sequence. In other words, E could be a foreign function, okay? So the whole setup of logical relations accounts for foreign functions. And an example of foreign functions that you see in computability theory are oracles, where people talk about oracles. That's just a foreign function interface. Okay? So in particular, even if I'm reasoning about ML code or something, the thing that I'm describing as a function could be some hunk of machine language somewhere. That's the thin edge of the wedge. That's the beginning of how one thinks about using logical relations to verify compilers and how to develop a theory of programming languages that encompasses other languages besides the one that is under consideration. Centrally important. Okay, so there's this idea that's being embodied here, which is sometimes called open-endedness. I don't constrain what can be a function. I only constrain how it behaves. That's to be contrasted with the natural numbers, because the natural numbers are an absolute thing. There's no such thing as a quasi-natural number that I get from somewhere else that isn't really either zero or successor. That's not in the game, all right? The natural numbers are the natural numbers. But functions just have to carry input to output, okay? That's also the notion of polarity, or positive and negative types, which I'm sure Noam Zellberger will mention to you next week. Okay, so that's one thing that we did, and then we proved a theorem about hereditary termination. So what we ended up doing, let me not write out the whole theorem, but one corollary was we got that this is hereditarily terminating and therefore terminating. Now we had to strengthen the IH, and I don't want to review that right now because I'll be reviewing it in a minute. Okay, now the other thing that we did, Dan did in fact, is he talked about logical equivalence. Okay, so he defined this equivalence, written like this, between closed terms of the same type. Okay, that was the idea. And the idea was that it should characterize observational equivalence, because observational equivalence, which is indistinguishability by any program context. Okay, two things are equal if you can't tell them apart. That definition is parasitic on what you allow me to use to tell them apart. If you let me use GDB, then nothing's equal to anything. Okay, there's no equivalences of any kind, because I can go down and pick around and look at what the machine code is. But the observations that matter are the observations that are written in the programming language itself. Okay, and then you say, for the purposes of my ML code, this expression and that expression are indistinguishable. So that's what's important about contextual or observational equivalence. All right, fixing what the experiments are is the critical move in the game. Once you decide what counts as an observation, then it induces a notion of observational equivalence. Okay, so that's the canonical notion of equivalence, because you'll remember it's the coarsest consistent congruence. So it's canonical. It's like the universal thing of its class. Okay, so that's the idea. So that way we know we're dealing with something non-arbitrary. Okay, because it's the coarsest consistent congruence. Boom. All right, that's the guy we're dealing with. Okay, and we defined it using context. Okay, so that's the way we did that. So the point of logical equivalence was to say it's very hard to work with. If I say to you, okay, now here's E1 and E2, tell me if they're observationally equal, you now have to think of all possible programming scenarios. Oh, okay. You start like wanting to take shortcuts. Of course. And the way you take the shortcuts is you say, oh, Genson's principle of intro and elim. The only thing that really counts is that I apply the elim operation to the type appropriate to the thing that I'm testing. Everything else, I could care less, right? If I've got a function in my hand, and let's say we had tuples around, I can stick it in a tuple and pull it back out, but I didn't really do anything with it. The only place where the rubber meets the road is when I apply it. Or the same with the tuple. The only place where the rubber meets the road is when I take a projection. So logical equivalence says, let's characterize their equivalence by contexts that are sensitive to the type. Boom. All right, that's the idea. So Dan gave you a definition, and now I'm going to draw a parallel. So Dan gave you a definition that says, well, what does it mean at nat? It means either, well, yeah, oh, that was good. Either we have E evaluates to some number, and so does E prime, or E evaluates to some successor, let's call that E1, and E prime evaluates to some other successor, let's call that E1 prime, and we have that E1 and E1 prime are also related as nats. Okay, so that's the definition. Okay, so the second part of the definition was tau 1 arrow tau 2 E prime. This says, well, when are these two things going to be equal? When they take equal things to equal results. Related things go to related results. Oh, okay, so we say if we have E1 is tau 1 related to E1 prime, you'll notice there's an obvious parallel going on here. Then we say this is related to tau 2 to this. And you don't mind that. Okay, and that was the definition that was given. And the point is it's a definition because it's given by induction on the structure of the type. Tau 1 and tau 2 are so to say prior to the function space tau 1 arrow tau 2. So I get to use them in their full generality in order to define them for the more complicated type. Here I define it outright by an inductive definition. What I like if I think of this as a vertical induction, then I like to describe that as a horizontal induction. There's a horizontal induction going on and a vertical induction going on. Okay, that's what's happening here. That's my way of visualizing it. Okay, so now you'll notice. Okay, so what was the main theorem? Well, the main theorem is that that if E is of type tau, the main thing you end up having to do is to show that it's self-related. Because it's not obvious that this relation is reflexive. Okay, you have to actually do some work. You can check that it's symmetric and transitive, I'm pretty sure straightforwardly, but it's not obviously reflexive. So the key thing was reflexivity, and the reflexivity was obtained by showing that it's a congruence. Okay? We know it's consistent by the way it's defined at nat, so we don't have to worry about that. We have to show that it's a congruence, and you can get reflexivity out of the fact that it's a congruence. So let's not worry about it. That's a little trick you can do. So the point is that because it's a consistent congruence, then it's contained in the coarsest consistent congruence. So that's one thing. So if they're logically equivalent, that's sufficient for being observationally equivalent. So that's it. That's the important part of the theorem, because it says if I can't tell them apart using a restricted notion of context, then I can't tell them apart with any notion of context. So there's content to that theorem. All right, that's what is essentially being said, because we're going to get from this that if E is logically equivalent to E prime, then it's observationally, I think it was written like that, observationally equivalent to E prime. Okay, that's what we're going to get. The converse is much easier, because if they're indistinguishable in any context whatsoever, then they're indistinguishable in this stylized way. Okay, so that's the way one would think about it. So in the end, they're going to be equivalent. So what's going to happen is we're going to get a characterization of observational equivalence via logical equivalence. And so it makes logical equivalence centrally important because it is the coarsest consistent congruence. It's defined in a funny way, but at the end of the day, it's the coarsest consistent congruence. There's only one. So it's the same as observational equivalence. Okay? So that's how that works. Okay, so that's a straightforward thing. This is the important theorem. Now here, the thing I want you to notice is that E is self-related at tau if and only if it's hereditarily terminating at tau. Just by the way I've defined everything. So really, I didn't want to prove anything about hereditary termination because I knew Dan was going to prove something about the stronger notion of equivalence, and then the reflexive case of equivalence is telling me hereditary termination, which means I have termination. Okay? So I get termination for free out of this. Okay? So you start to see that what is the moral of the story? If you establish a strong invariant, The theorem you actually have to prove, as before, is stronger than this because of the induction. But if you establish a strong invariant about the behavior of well-typed programs, then you can peel off all sorts of results. Now, sometimes those things are annoyingly called free theorems. I was thinking about this this morning when Dan was speaking or when Ed was speaking. But, you know, yeah, it's free in the sense that stealing stuff is free, okay? If you prove all of this theory and you develop logical relations and you prove all these theorems, yeah, then all sorts of boring things are free, okay? But it's like theft, okay? It's not free at all. There's nothing free about it. It's hard, bloody work, okay, to invent all of this stuff that I'm showing you. So you'll know as you work through it, these are not free theorems in any way at all, okay? That's simply not true. It's simply the observation, which was already known for quite a long time, that types induce behavioral specs. Okay, so that's a recap and a consolidation of things we did last time. Okay, so, all right, so now what I want to do is extend this idea to polymorphic types, because we get a lot of use out of this. Okay, so the way we're going to do this is recall that we started with a system called T, whose types were, which I've been using already, but just to remind you, all right, tau 1 arrow tau 2, and whose expressions, well, I don't feel like writing them all out. Okay, so we gave those last time. So we gave system T, which has higher order computability over the natural numbers. Okay, so that's the important thing. And by the, yeah, okay, I'll get back to some other things about that later. Okay, so what we're going to do is we're going to extend to what is called system F. Okay, and all system F does is add in here polymorphic types for all t tau. So these are all things you were discussing this morning, so I'm assuming this is all pretty safe territory syntactically. Okay, I was preparing my lecture. I didn't go to Dan's lecture this morning, sorry. Okay, we have two different forms of expression now. We have a type abstraction, and we have a type application. I'm not sure what notation was used. So this is called type abstraction, and this is called type application. By the way, everything I'm saying is in the book under the chapter called, oddly enough, parametricity. So you can have a look there. So there's no need to transcribe. Everything's written down, and I'll try to be largely consistent with that if I can. Okay, so that's the setup. That's the setup. So we now have function types, polymorphic types, and the type of natural numbers. Now, I don't know whether Dan talked about polymorphic definability of like natural numbers and stuff. No? Okay. Then I don't need to make any remark. It's important to have what is called a positive type, as I alluded earlier, amongst these types. These are both negative because, as we're going to see, as I mentioned to you before, this is characterized behaviorally. It obeys the call and return sequence. This is going to be characterized behaviorally. But if you want to have a notion of observational equivalence, you have to have some positive result that you can look at. So you need a positive type, like the natural numbers, to count as your observation. So that's why I build those in. Lots of time, oh, and I left something out. And lots of times people will omit that. It's not a good idea, okay? The other thing we have is a variable type as another form of type. Because you see, I have quantified types. So as you saw this morning, you can form the type for all t, t arrow t, which means focusing here, I have type expressions that involve type variables, or as they've been historically called, variable types, however you like to think about it. They're types that vary, okay? So that's the thing you were discussing this morning. And at this level of discussion, there's been lots and lots and lots of popularizations, and so you can probably find lots of popular accounts of all these things, and I don't have to repeat them here. However, what I will mention is I will remind you, and I think this might be, this will be worthwhile at the end of my lecture, is System F latently has existentials. I don't know whether this was made apparent to you. Okay, you can define this as the polymorphic type that says, it goes like this. Let me just write it out. Arrow U. Okay, that's the type. The idea is that, and this is very important, the client is polymorphic. You see, because If this were like exist a type with some like insert and remove and I don't know what, empty and some other operations, what the client knows is it computes a value of extrinsic meaning, like a number, let's say, using an unknown type supporting the operations described by tau, like get, set, or insert and remove or whatever they were, okay? So the critical thing is the client is polymorphic, okay? And I'm going to use that a little bit later, okay? Polymorphism is the essence of data abstraction. That is what modularity is all about. Everybody and his brother in programming languages claims that they own modularity, okay? Nobody's got a theorem but us, okay? So the theory is based on polymorphism. If you don't have polymorphism, you don't have modularity, or you're just blowing smoke, okay? So the thing is, I want to show you that there's a rigorous theory developed by Reynolds originally. That's who I'm this lecture should be considered an homage to Reynolds. And so I'm trying to draw out some important points. In particular, polymorphism is inescapable if you're going to have data abstraction, okay? Another way of saying it is, there's no other competing theory, okay? People can claim all they want, but let's put our money on the table. There is not another mathematical theory of data abstraction. This is it, okay? So that's important. Okay, good. So, good. So that's the syntax we're setting up. So the question we have is, okay, over what do type variables vary? This is important. If they're variable types, over what do they vary? So that's an important preliminary question and then the real question is how to extend the notion of logical equivalence. It's easy. Observational equivalence is defined in exactly the same way. You consider all the contexts that give you a natural number as an observation, and because now we're in system F, so those contexts can do polymorphic application and instantiation and stuff, application abstraction and all that. But anyway, the definition is formally the same. It's just that the contexts are now in the enriched language. So that's no question about what that is. So the question is how to extend logical equivalence to polymorphic types. Okay, and this is, for reasons that I'll explain here, will give you an inkling about what to explain here. Okay, so the idea is this. When I write lambda t dot e, and it has a type for all t dot tau, and we say this is true if when t is a type, e is of type tau. In other words, it's somehow quantified or has an abstraction over an unknown type. So this is the notion of a variable type, okay? So that's the critical idea, right? The typing rule boils down to that, okay? This is the critical idea. So the question is, over what does t vary? T is a variable type, over what does it vary, okay? So let me now, I will explain to you why this is an important question, because it's directly related to the question, which I'll write over here below the line, is skipping the other parts. How do I define for all t tau? Okay, what should the definition of that be? It's completely related, okay? Because what we're going to do in the first instance is we're going to think of these things as being of this type, and then we're going to try to define what logical equivalence is somehow or other by induction on the structure of this type. That's what we ought to do, right? If we're following the pattern, right? You got my gist, right? Makes sense? Because this next passage here is critical to understanding everything. The essence of the whole idea is what I'm saying right now. The rest is technicalities. There's a big pile of technicalities. You got to get used to throwing around some machinery, but I'm telling you the ideas, okay? So these are the ideas. So the question is, how do you define this? So here's what anybody and their brother would do, okay? If I just sat you down and said, you have 10 minutes, write it down, okay? Well, the only thing you could possibly guess is you would say, well, let's define this as for every type sigma, I'll use sigma and tau both for types in this lecture. So for any type sigma, I would expect E applied to sigma, because you see E and E prime are polymorphic, should be related at what type? Sigma for t tau to E prime of tau. This is exactly what you would think, because you see it follows the pattern, which is inconveniently obscured here, For functions, it's some kind of a function. It takes an argument, gives a result. So you say, well, for any argument, I give you a result. So obviously, something which is polymorphic is some kind of a function that if you give it a type, gives you a value of that type. So if I put you under the hot light and locked you in a room, then you would probably come up with this. And sadly, it doesn't work. Okay? For those of you who haven't seen the proof before, so please sit on your hands if you actually know the answer to this because you've seen it before. For those of you who haven't, who are seeing it for the first time, can anyone think of like what is wrong with this? So this is bad. Okay? Why? Because it's ill-defined. That is, it's not properly defined. So it's bad because it's ill-defined. Can someone who doesn't already know the answer intuit what is the issue? Could someone say who's speaking? You are.
Is that tau supposed to be there on the right-hand side, or should that be a sigma?
What's that? So?
Are you, E prime of tau is up there? Was it
Sigma. It should have been sigma. Yeah. Yeah, it should have been sigma. I made a mistake. It was just a typo. Sorry. Yeah.
That wasn't it.
Right. You think? What's that? Yeah.
That wasn't it.
Okay, that was not the problem. No, that's the stupid problem. No, there's a serious problem. It's not a stupid problem. Yeah.
Could it be that for all is not part of the logical theory?
Could someone relay what the?
I think he said. Could it be?
Like I was thinking of the logical theory that you can form your for all sigma.
So could someone? I didn't fully hear the question. What's that?
I think he asked, is there a metalogical theory that you could formulate this in? Is that?
No,
He said, could it be that for all is not in the theory that we're using right now and that we would need to put it in some sort of metalogical theory?
I don't like those terms, but there may be something to that. But let's debug this definition. Okay. I don't know. I think you were next.
Is it not well-founded?
It's not well-founded. Yes. Is that what you were going to say? Yes. It's not well-founded. Is that what you were going to say? What was that he said?
I was going to ask if you're allowed to quantify over type.
Yeah, so that's the issue, right? Okay, good. You're on the right track. Okay? The reason is it's not well-founded. Remember, what we're doing is we're trying to define, the key to this whole thing is we define this by induction on the structure of tau. That was the whole game, all right? That's how I'm doing everything. The problem is that sigma for t tau is in no sense, and I'll show you exactly why, a piece of, I don't know what to say, a piece of for all t tau. Okay, it's not like already sitting there. You see, when you have a compound type expression, you can refer to chunks of it, like with tau 1 arrow tau 2, then I can take tau 1 and tau 2 as given. They're already sitting there, and then I make a bigger one. But when I take the quantified type, the things I instantiate by, it's not so obvious that they're smaller. And I'll tell you why. So for example, tau, we'll look at for all t, consider for all t, t arrow t. So that's the as we have over there, where this is my tau. And now take sigma to be that very thing. So now when I plug in sigma for t, t arrow t, what do I get? I get sigma arrow sigma, which is for all arrow for all. Okay? And if you examine this as some kind of syntax tree, you're not going to find itself, arrow itself, in somehow implicitly in that syntax tree. It doesn't exist. Okay, yes?
So can you solve this with like universes or something?
What's that?
Can you solve this with like universes or something?
Yeah, so I'll paraphrase your remark. Okay, so there are two possible moves. One, which will still be wrong, but even for a more subtle reason. Okay, so there are two possible moves. So let me figure out where to write that over here. So there are two moves. So the problem, it has a jargon name. The problem is what is called impredicativity. It's a jargon word. It goes back to Russell and Whitehead. Okay. It's just the phenomenon I'm describing to you, okay? So there are two possible resolutions. One is make it predicative. What does that mean? And this is actually what Dan was doing this morning. He was showing you could get away with this to some extent. Okay? What is it you do? Is you say that type variables range over, oh, I don't know, I'll just use a word, small, don't take that to have any particular meaning, and you regard quantified types as large. Now, when I form, so the sigmas, oh, how did that work out? Sigma stands for small. So if I quantify over all small types, then that rules out this example, because I'm trying to use a big type to plug in for the type variable, which is supposed to be small. And then you think, oh, maybe that will work. Yes, it will work, but it's the wrong idea. Okay? And I have to explain to you why it's the wrong idea. That's coming up. Okay? So that's the second degree. So I can make this ill-defined by doing something about smallness. Make it well-defined. What did I say? Make it well-defined by considering some idea of a small type to instantiate the quantifiers. Okay, that's possible. But I can do that even properly, but merely doing what I said here, although it's well-defined, it's the wrong guy. Okay? It's not the relation I want. And the best way to explain that is to look at the other solution. The other solution is to think hard about variable types. Now, what do I mean by that? Well, let's go back to what I said to you a few minutes ago in order to get your mind going in the right direction. When I told you what is the semantics of the function type, I specifically emphasized I don't care what the function, so to say, physically is. Okay? I only care how it behaves. All right? I don't demand that it be a lambda in my language. It could be a foreign function. This is good, right? This is good stuff, okay? It's interesting, by the way, that the math underwrites the horrible sounding engineering crap of foreign functions. Okay? So that's a nice thing, because if you're doing your theory right, it's totally applicable and accounts for everything in a clean way, and things have definite answers, and that's the end of it. Okay? That's like my whole career is all about. Okay? Answering damn questions once and for all. Okay. All right, so what I said was we don't care what the function actually is. So if you look at what I'm doing here, even if I do that small hack or not, what I'm doing is I'm saying type variables range over type expressions. The syntax. Okay? That's not what I want. That's what's wrong with the thing I'm going to do here. I don't want that. What I want to do is I want to say that type variables range over, well, for lack of a better way to formulate it, all conceivable types. That's kind of a tricky business. All conceivable types. Not just the ones you can write down in this particular language. So this is also another aspect of foreign functions, because it's one thing to talk about foreign functions on int to int or word to word, let's say, which are very, very concrete. It's another interesting thing to talk about combining two programming languages with completely different, superficially anyway, syntactically different type systems. How would you make them interact? It's not a matter of kludging your compiler to make some goddamn cockamamie thing sort of work. That's not the idea. The idea is, what do we mean by types that they have in common? What is the master theory of types? That's the important point. Even the ones I can't write down because maybe they're being imported from a different language. Oh, all right? That's a different idea, okay? So what do we do here, okay? Not just the ones you can write down. So I want to think about that. So what are types in the setup that I'm developing with logical relations? What is it that I've been saying? So now comes the very important point. And then everything else I have to say is a technicality. Like, to do this stuff right, you have to know what the ideas are, and you have to be able to sweat the technicalities. The thing that you have to learn as a beginner is don't sweat the technicalities too much. Get the idea of what's going on. Okay, so you can easily get lost amongst all the technicalities. Okay, so what is the idea? So the idea is that types are certain, I'll say what I mean by that in a minute, relations. Okay, that is the idea. Because you see, what do I do with, when I looked at this thing, this is a binary relation, in the case that I've done it so far, between expressions of type tau, let's say. When I talked about hereditary termination, I looked at a unary relation, or predicate, on type tau. Let me just write it like that, type tau. Okay? So the idea is that I'm interpreting types. What I'm doing is when I say, the full form is a little more complicated, but when I say something that has that syntax, that implies that, let's say, it's self-related, it's in the relation, I'm interpreting the type as a binary relation, and I'm telling you that it's reflexive. Okay? So the types are being interpreted as binary relations, and the definitions of these relations is given in terms of their execution behavior. Okay? That's what's important. So what I'm going to do is what I mean by certain relations. So what we're going to do is we're going to introduce an abstract term called an admissible relation. Okay? And the idea is that the exact definition varies. Varies with the application, whatever you're trying to do. It has to do with the language you're dealing with, and so on. For example, next lecture, I think I'll talk about PCF, and we'll have to deal with some issues to do with recursion. So we have the general idea of admissible relation. But what I'm going to do is I'm going to demand that it respect equality, that is, observational equivalence. So I'm going to demand that if we relate to things, and E1, and let's say this is some tau 1 and this is some tau 2, is in general I'm going to allow heterogeneous relations, and I'll show you how that works in a minute. So we say if this relates, or in other words, E1 R E2 if I write it infix, and E1 is observationally equivalent to E1 prime, and E2 is at the appropriate type, tau 1, and E2 is observationally equivalent to E2 prime, then I want to know that this holds if and only if R holds of E1 prime and E2 prime. In other words, I'm relating things modulo their observational equivalence. I treat the equal things as indistinguishable from the point of view of the relation. Lots of things can be varied for different applications, but for my purposes, this is what I want. Okay? So this is what I'm going to do. So I'm going to consider the class of admissible relations. So what is an admissible relation, just to be accurate about it? What we're going to do is it's going to consist of 3 pieces of data. I'm going to look at binary relations only because the n-ary case is just like bureaucratic excess. The unary case can be obtained as a special case. So let's just look at binary case. That's the interesting one. So we'll have a domain type. We'll have a range type. And we will have a binary relation that respects a binary relation between expressions of those types. So I will write that as R relates tau 1 to tau 2. If this is tau 1 and that's tau 2. Okay, I'll write it like that. Okay? Such that I want respect for observational equivalence. Okay, that's the thing I want. For technical reasons, which I'm going to develop in a moment, I'm going to need an additional condition on admissibility for the purposes of the proof. And then when I'm done with the proof, we'll see that the additional condition actually isn't additional anyway. Okay? So that's what we're going to do. Okay, good. All right, so that's my notion of admissible relations. So now what I want to do is revisit the definition here. So even if we manage to get ourselves out of trouble mathematically, we don't want to go in this direction. This is not what we want to do. So what we want to do is to express the full possible force, the full meaning, okay, the full meaning of type quantification. I want to extend my notion, okay, to account for, so here's the first cut at what we do. So this has to be fixed to make it technically right, but here's the first cut. What I will do is I will say, what this means, and I'm going to have to modify this, but here's the first cut. I don't want to consider, or let's call that tau like I did before. I don't want to consider only syntactically defined types. I want to consider the quantifier to range over all possible types. And those possible types are going to be admissible relations, which are heterogeneous. They relate disparate things. The reason I want them to be heterogeneous, I will show you later, okay? It will emerge, okay? So approximately what I want to say is, in quotes, for every R which is admissible, so this, by the way, is sometimes called a type candidate. That was Girard's original terminology. We can call that a type candidate. It's something that it's a candidate for a type. It's sufficiently type-like to count as a type. All the actual syntactic types will be type candidates, but there are more candidates than there are actual syntactic types. That's what's important. Okay? So we'll say for every R admissible, what we're going to say is E is related at tau, or you can feel that there's something going wrong here, okay, T, and I'll write it modulo T is R. Okay, and I'll put close quotes around here. So what I'm going to do, notice, this has a free type variable in it. So that's why I have to have a second cut to really nail this down properly. But here's the intuition. The intuition is, let the quantifier range over all possible types, not just the ones you can write down in syntax, and demand that E and E prime be related modulo the fiction that the meaning of the type T is R. Oh, you see, when you were doing the earlier definition, what you were doing, now let's retrofit. What you were doing is, when you did it with sigma for T tau, you were demanding that R literally be twiddle sigma. You weren't allowing it to be anything else. It had to be twiddle sigma, because when you plug in the sigma here, the definition that would be compositional, and then when you get to where the T used to occur, it would be twiddle sigma, and that's the relation you're talking about. So the additional degree of generality here is I quantify over all possible R's, one of which actually might be twiddle sigma. But let's not worry about that right now. When I prove the identity extension lemma, we're going to take advantage of this. But let's right now do this. So we do not restrict our attention to this. So the way to think about it is, so I have to, second cut will make this precise, but the way to think about it is this. There's this big universe of all possible types, which are binary relations between pairs of closed types, which are the values that they relate. So let's put them in here. It's a big stew, okay? So here's a dumpling, okay? And here's another dumpling, so that's R1. Here's another one, that's R2. And here is R3. And these go on, well, there's quite a lot of those. It's hard to draw because there's uncountably many, okay? So because what we're doing is we're taking the power set of a countable set. So we're doing 2 to the countable set. So there's uncountably many here. So we can think of this as all possible types equals all admissible relations, which is essentially all subsets, almost all subsets of a product of terms, that is pairs of terms. Okay? So I've got this big soup here. That's all possible types. Amongst all the possible types are things like twiddle gnat. That's in there. Okay? And maybe here is twiddle gnat arrow gnat. But maybe here is something that nobody ever heard of. Okay? In other words, you've never written it down syntactically. Not only that, you can't, because these relate to things of the same type. But these relations in general relate things of different type. Why do I want to do that? Representation independence for abstract types. What Dan showed you is you can have a reference implementation and a candidate implementation, and you can prove that the clients don't care by having a simulation relation that says the representation of the reference is related to the representation of the candidate, and then you show that the operations preserve the fiction that those are equal. They're pseudo-equal. Okay, so did he do like two queues or something like that? Did he do queues with two lists, or Dan? What did you do? Is Dan here? No. What did Dan do this morning? Oh, there you are. What? Oh, two counters. Okay, fine. All right, but the point is, there's two completely unrelated pieces of data, and you count them as equal. You relate them to one another. You have a simulation relation between them, and you show that as far as the operations are concerned, they are equal modulo the fiction. Okay? And then, because of the miracle of polymorphism, which I'll get to in a minute, that tells you that the clients can't tell them apart. Bingo, now you have a theorem. Okay? Beautiful. So the whole idea about abstraction and modularity is based on a theorem. It's not a methodology. Okay? I like to say, a methodology is what you're stuck with when you don't have a theory. Okay? So we don't want to have methodologies, we want to have theories. And then we apply those theories to like get work done. Okay, so that's the idea. So rather than wave hands about representation independence, it's a theorem. Okay, so what we do is we say E is related to E prime according to the way tau describes it, except that whenever you see T, the relationship is defined to be R. That's my little fiction. And when I quantify, I allow all possible R's. So I demand that something that's polymorphic type be well behaved even on types that it couldn't possibly ever have known about in advance. Notice the analogy to foreign functions. I don't demand that functions, only, accept arguments that are written in the programming language that it likes. It accepts anything, and it just behaves the right way. Well, the same thing here is that the uniformity of polymorphic things depends on being extremely uniform. They have to be really oblivious. Okay? The miracle is they are, because that will be the fundamental theorem, is that it's true. Okay, so that's the cool thing. You might imagine a priori that we're demanding too much. If we're demanding of a piece of code that it be completely oblivious to any type, even ones it couldn't have dreamed of in a million years, you might think that's too much to ask. But it's not. The Reynolds' theorem is it's not. That's the important thing. Okay? So that's what we're going to do. So this is all possible types, amongst which are the, so to say, actual types, but we're going to allow a lot more. That's the picture to have in mind. Okay, so how do we now make this precise? So in order to make this precise, I have to define a more general kind of relation, which is heterogeneous, that is type heterogeneous. Okay? So what I'm going to do is I'm going to define the following idea. This tau E prime brackets, I'll use this notation, delta to delta prime. This is what I'm going to define. Okay, and what is the idea? The idea is that, okay, well, first of all, let's get this out of the way. So delta takes type variables and gives them meaning. So it sends T1 to, let's call it sigma 1, Tn to sigma n. And delta prime is another environment that takes type variables to their underlying, what they're going to range over. And what does eta do? Is it sends each one to an admissible relation between sigma 1 and sigma 1 prime, and all the way down, it sends it to an admissible relation, let's call that R1, and then this would be Rn, and then sigma n related to sigma n prime. Okay? And these have to be admissible. Okay? Okay, it's an admissible class of relations. Okay? So that's what we do. So if there were only one type variable in play, this would be a relation between one type and another. That's how the other thing I wrote over here in quotes is a special case. Do you see that? So I want you to not get lost in the technical machinery. There is a bunch of technical machinery. It's unavoidable. But if I talk you through it, I believe, properly, then you won't get lost in all the details. Okay? So this is just allowing for multiple type variables to be in play at once and to consider for any particular choice of the meanings of those type variables, I can choose a relation to interpret it. That's all that I'm doing here. Why? Because for the sake of the induction, I'm going to always get more and more type variables, so I define them like that, okay? So that's what I'm doing there. So that's how I'm going to define that. And how do I define, oh, and then what do I have? I have that E is of type, oh, I write it like this, delta hat of tau, and E prime is of type delta prime hat of tau. So notice these are of disparate type. Well, why? Let's, a good like seat of the pants thing to keep in mind is, think of a representation independence proof. I'm the client of an abstract type. So I have an abstract type T, like the counters, which on the left-hand side is one implementation, and on the right-hand side is the other. The code I'm actually running is the increment and decrement, or the operations for one representation. In turn, on the other side, I have the increment and decrement for the other operation. So really, the code I'm running, what's happening is I have two different types going on. The reference side and the candidate side, and those are of disparate type, but they're tied together by the fiction that the simulation relation, quotes, equates them. Okay, just put that in quotes. Consider those to be equal. There's a fiction that those two representations are equal. Okay, so that's what I do there. Okay, so let me write it on the left half of this board so that we can keep everything on one board. Okay, so now how do we define this? Okay, so first clause is, what about a type variable? What do I want to say here? E is eta of t related to E prime. Because my assumption is, now this is, E is of type delta of t. So remember, this is of type delta of t, because delta hat of t, the base case is, when you get to t, it's delta of t. This is of type delta of t, delta prime of t. And eta of t relates them. That's my assumption about how it's set up. So the idea is that if I get two values of the abstract type or the polymorphic type, we'll consider them equal if they're related by the current fiction that I'm maintaining. Okay? You see what I mean? All right? That's the idea. So we're keeping a correspondence. So if you like, read this word as correspond. Read the symbol relation as correspondence. So E corresponds to E prime at type T if the relation assigned to type T says that they correspond. That's a way of saying it. Okay? So it's a correspondence relation. Okay, so that's what we do there. 2. What do we do at NAT? Well, we behave exactly like we did before. E evaluates to Z and E prime evaluates to Z, or E evaluates the successor of E1, E prime evaluates the successor of E1 prime, and, well, they're related, okay, at NAT, E1 prime with the same data. Writing like that. So I'm just repeating the definition we gave before, and in fact I'm going to repeat it also for function types. So, by the way, so I read this as corresponding modulo eta, or eta equal modulo eta, or whatever. So eta is telling us the relations by which modulo that fiction, they're the same. That's the way I think about it. Okay, and what do we do here? Well, we just do the same. We say if you give me tau 1, it's a smaller type, tau 2, let me just write eta for shorthand, implies E of E1 is related at tau 2 to E prime of E1 prime, well, E1 prime should have been. Okay, E1 prime with eta. I just won't repeat the typing information. Okay, right like that. And now the critical thing. The critical thing is how to say it properly. for all t tau e prime mod eta, okay, this is our related mod eta, if and only if now what? For every sigma 1 and sigma 2, for every relation between sigma 1 and sigma 2 which is admissible, so everything is kind of parameterized on the criterion of admissibility. I want to do that because it'll help with other things, okay? So I want to do that, okay? And now what do we demand? The interesting thing is this, is we demand that E at sigma 1, is that what I want to say? I believe this is what I want to say, and I have to check my notes. Let me think about that. The important thing is that this is T. Right, this is going to be good. And I have to double check. I believe this is right. So, okay, let me, I like to invent it with you, so let's do that. Okay, so because of the way I've been using my notational conventions, let me write it sigma, sigma prime, so that it'll all line up notationally. I'm not really changing anything. Do that at T. So notice, I'll come back to that in a point, where I extend E by T being R, and I extend delta by T being sigma. Yes, I'm good, yep. And I extend delta prime by T being sigma prime. I believe I have the right definition. Okay, good. It's, I think it's, I like to, when teaching, I like to be 3/4 prepared, because that way I have to think it through while I'm telling you, and it helps, okay? All right, so I think I have it right, okay. So the critical point is here. This has free t's in it. And moreover, t is, so to say, a piece of for all t tau. I've gotten rid of that quantifier. I've taken the syntax tree that has for all t tau, and I've extracted t from it. That's a sub-expression. So we're good, right? Previously, it's been erased now. Previously, yeah, it's been erased now. Previously, we were substituting in, and then we got into all sorts of trouble. So here, I really do go to a subsidiary, just like here. I go to a subtype expression, a type expression that's a piece of the one I'm given, okay, and relate them there. But the meaning of T is any R between any two types that I choose. Any R in the class of relations we're considering. So in other words, I demand that they be equal uniformly in all conceivable types that could ever come down the pike, ever. Okay? And why do I say it like that? Because I will choose the conditions of admissibility to be as general as possible to make the proof of the main theorem go through. Okay? So that's the idea. And then it's maximally flexible. Okay, so that's the idea. Okay, if you get nothing else out of this lecture, that's it. Okay, that's the idea. That's the entire idea of parametricity is right there on that board. It's the extension. Everything else now, I'll tell you, is cranking out work. Okay? All right? So what we do is, the point is that we enlarge the domain of quantification to include all possible candidate types, which are relations of a certain class. And we demand uniformity with respect to all that general of an interpretation. Then, what does that mean? If I have something which is polymorphic, I can now start jamming in relations for the polymorphic type and pump out all sorts of properties about the polymorphic function, like Dan was doing this morning, for free. Okay, for free, yeah, right, for free. It's not free at all. It's based on Girard, it's based on Reynolds, it's based on Tate, it's based on lots of work, and lots of work that you ought to do in order to verify for yourself that this is the case. So, yeah, it's free, whatever. Okay, so that's the critical idea. So, and in fact, of all of them, so this part you could say is Tate's idea, and this part you could say is Girard and Reynolds. Girard actually did it for something morally equivalent to hereditary termination. There are some technical things let's not go into about that, okay, but morally it's hereditary termination. And for whatever reason, he didn't think about equality, and it was Reynolds who thought about equality, okay? And so it's Reynolds's contribution to realize that it gives us results about equality of expressions of polymorphic type. That's what's really important. Now, curiously, Reynolds's actual paper on this was flawed in a way that doesn't really matter, okay? Because Reynolds thought that you could interpret types as sets in a very straightforward way, that the meaning of tau 1 arrow tau 2 is all set theoretic functions, and the meaning of for all t tau is you quantify over all sets, basically, or all relations. That does not work. I mean, he later proved that that's, in fact, wrong, erroneous. It's positively erroneous, okay? That's an interesting point, just as an aside point, because it shows that there are phenomena that are useful and important, that are mathematical in nature, that are applicable only to computation. Types are not sets. If you get the idea that somehow types are just talk for sets, you're wrong, okay? And this is a spot where the issue comes to light, that it's positively wrong. It's not like, oh, doctrinally you shouldn't speak like that. No, it's not that. It's positively wrong, okay? So that's a fascinating thing because it means that, my own interpretation is, it means that constructive mathematics is much richer than classical mathematics. And that's good because it's all about programs anyway, and I'm a computer scientist, so good stuff, okay? This is what I like, okay? So this is what I live for. So it doesn't all just reduce to classical math. So this goes back to my earlier complaint about what students, throughout the US anyway, are taught, as freshmen about the theory of computation, leaves out a lot of important things. In the fullness of time, that will all get corrected, I'm sure. Okay, so, all right, so this is the definition. Now let's just rattle off a few things that are true about this definition. I'm not going to drag you through the details of proofs because it will never work at the board. So, but it's all in the book. Oh, it's so nice. Usually when I lecture at summer school, it's like everything either comes out of my mouth or that's it. And now it comes out of my mouth, but it's written down. So you can go and look it up. So every detail is in the book. Okay, so the main theorem, it's the one I quoted to you before. And then there's an elaboration of it. But the main theorem is this. If this is in system F, okay, then guess what? If it's a closed thing and it doesn't have any free type variables, it's related to itself at type tau, modulo nothing. Now, to prove this, we have to strengthen the hell out of it, okay? We have to consider, okay, so the proof is more involved. The proof requires considering two additional things. One is free type variable, so we've kind of alluded at that already, how we do that. And moreover, free, so to say, term variables or ordinary variables. And I showed you last time how you come up with that, okay? So you prove a much stronger theorem to make the proof go through. And the important thing that the proof requires is it requires that admissible relations be closed under head expansion. Under head expansion. I need this. And the reason is, I'll review it with you why that's the case. If you go through the proof, here's what happens to you. When you look at, for example, the case of, you want to show, okay, so what we want to show is what we know. I won't have room here, so let me start it on a different board. Okay. So this is part of what I was saying about admissibility. So the way this game is played is you choose what are the admissible relations to suit your purposes. Okay? That's the critical idea. Okay, that's the critical idea. Okay, so so here's the idea. So here's where the spot comes. So what I want to do is I want to show, I'm going to cut to the chase to get to the main point. I want to show that sort of lambda xe is related at sort of tau 1 arrow tau 2 to lambda x e prime modulo some eta, which is available and active at the moment. This is a critical spot in the proof, okay? So what I have by inductive hypothesis is the following thing. If E1 is tau 1 related to E1 prime modulo eta, then I know, because when I strengthen it appropriately and so on, then I will know that E1 for xe is related at tau 2 to E1 prime for x e prime mod eta. Whoops, sorry. Mod eta. Okay, this we will do. Okay, so that's what we have by IH. Okay, now the definition of this says we suppose that we have an E1 which is related to E1 prime mod eta. Okay, and what I want to show is, and that's the trick, lambda xe applied to E1 is related to lambda xe prime applied to E1 prime mod eta. That's what I want to show. Okay? So the thing is, I have this, but I want that. And the critical thing is, this head reduces to E1 for xe, which is this guy, and this head reduces to E1 prime for x e prime, which is this guy. And the thing they reduce to is related, so I demand that the things they reduce from be related. That's my criterion of admissibility, okay? In this particular case, that's what I'm doing, okay? So that's an example. I'm just showing you. Part of the game is, you know, you figure out the proof and then you choose the criterion to suit your purposes, okay? So that's what is going on here, okay? So the idea is that very often it's standard in any kind of math. If you just read the math, it's, you know, everybody like seeks to cover their tracks, right? They just write down, here's a definition, here's this, here's da, 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 da. Suddenly, magically, exactly the right thing happens at exactly the right moment. And you can't deny that it all works, but you don't know how to invent it. Nobody ever tells you how to invent it. So what I'm trying to do is tell you what people actually do when they're trying to figure this out, and then they cover their tracks. So, okay? So this is the reason why you want the closure under head expansion, because you have to make the proof go through. Okay? All right, so that's an example, okay, of where that comes from. So this is the main theorem that tells you things are self-related. Then we can pump out, I want to say something else, and then we can pump out consequences of things being self-related, okay? So, and Dan did this this morning, okay? When you know things are polymorphic, then it means that the type variable, the variable they're polymorphic in, is very generic in the sense that you can interpret it by a relation. And if you interpret by a relation, then you'll get the kind of results you want by choosing that relation appropriately. Okay, before I do that, I want to do something else. I want to mention what is called the identity extension lemma. Okay, and the idea is the following. I'll write it in quotes because the technical version is this. If all type variables are interpreted, I'll just write it like this. It's in the book in technical form, are interpreted as observational equivalence, then the resulting relation, that is, then logically related things are logically related things are observationally equivalent. In other words, you have a bunch of type variables, T1 through Tn. If you decide that these really mean tau 1 through tau n, and that the relation in question is that they're equal, then what you will get out is E is related to E, which means that they are, which the identity extension says they will be equal, observationally equal. So in other words, if you interpret the relation, one of the choices you have for the relation is to relate tau 1 to itself, plug in tau 1 on both sides, make those things be equality, then the relation you're defining is equality. In particular, if there are no free type variables at all, then related things are observationally equal. Boom. So it's a sufficient condition for observational equivalence. Okay, do you see that? Do you see my reasoning? Okay, I want to show, remember the whole game was to show, and I can do this more generally, E prime, and I can write this E prime. I can write it like that. The whole game was to show that logical equivalence is a handy sufficient condition for observational equivalence, because observational equivalence is very hard to reason about directly. So I want to prove that theorem. The way you prove it is, because there are polymorphic types involved, if the polymorphic types could be interpreted as any relation, then this clearly can't hold, because I could just relate 2 to 3 as natural numbers, and then, of course, then the output won't be equal. Okay, that's not going to work. But if I say that all of the abstract types are interpreted by the identity relation, everything is just equal to itself, then the results will be observationally equal. And in particular, if there are none, if n is 0, then logically related things will be observationally equivalent. So it preserves the identity relation. That's called identity extension lemma, and that's something that Reynolds formulated. Okay? Good. So that's a very important thing. And now let's go back to the abstract types. I will do that on this board. I have a feeling I'm overloading most of your circuits. Yes? Any questions? Just interrupt me, please. It's completely normal to be buffaloed by this the first time you see it and the first 10 times you see it. But eventually it will sink in and you will achieve enlightenment, okay? And then you will understand, okay, what's really going on with type theory, okay? So this is, theory of logical relations is what's really going on in type theory, okay? That's keep this in mind. That's what's important, okay? And everybody and his brother and sister are taking advantage of this at the moment, like big time. I mentioned earlier before, with like compiler verification problems, okay? What you do is you relate source and target language. The relations go between 2 languages. It's the same basic idea. Mal will be telling you all about this, okay? It gets to be hell on wheels, I will tell you straight away. If you think this is complicated, you haven't seen nothing, okay? Because by the time Patty and Amal are through with you, all right, you'll be melted into a little pool of butter, okay? Because there's a lot. So as I mentioned in the very beginning, our goal here is to tell you stuff that you're going to be told again, okay, by another lecture. But hopefully by that process of enough water running over you for enough time, you'll get eroded down and you will at least accept it, okay? So try to master this that I'm telling you, because everything's written down in the book. Master those main ideas, and then you will see when Amal does crazy things and Patty does really crazy things, they're all the same thing, really, okay? But they're jazzed up very substantially, okay? So that's what you want to keep in mind. Okay, that's the best I can do. I'm trying to give you the inside game. So now let's go back to abstract types. So we had an abstract type. Now, if I had bothered to do my homework, I would have remembered this with Dan. But he had something like what? Ink goes from T to T. I don't know. Dec goes from T to T. Somebody help me out here.
0 increment.
What's that?
0 increment and value.
You have 0, which was that?
0 is T.
0 is T.
Increment T to T. And then
Increment T to T.
And then value.
Value, which is exactly what I was going to write. Great minds think alike. We've been working together for so many years, I even know what he would write. Okay, so we can write, and this is like just nat or int, nat or something?
T to nat.
T to nat. Oh, yeah, T to nat, yeah. T to nat. So this must be, oh, it's just T because it's 0. Yeah, okay, fine. Is that right? Okay, that's good. Okay, so that's your abstract. Let me write the 0 up here so I can put it on one line. Okay, good. All right, so that's the abstract type. Okay, right? So as I mentioned earlier, what does a client of this abstract type look like? So the client has the following type. Okay, the client has the type, it computes something of a result type row. So the client has the type for all t, and now I'll curry it. It'll help me to curry it. Okay, if you give me an inc, an increment, and you give me a decrement, and you give me a val, and you give me a 0, I'll give you a rho. That's what the client looks like. This guy, remember, is is for all u, this type, let's call it sigma client, okay, written like this. Well, it would be u here, so let me write it as u. So then this will be sigma client, which involves a u, arrow u. Okay, that's the way to think about it. So what happens is the data abstraction applies, it is applied to rho and the client code. So that's what will be here. So I don't know what to write here. So the client is actually rho for you, that, let's put it that way. Okay. Okay, so you pick rho and you pick the implementation of the abstract type, and this guy is going to run it. So I'm screwing that up, I think. So let me just continue my story here, over here. The important thing is that the client is polymorphic. That's what I want to get at. So let me plug that back in. I'm aware that I'm short of time. So the client looks like this. So what does the client say? The client is polymorphic. So the idea is the client is uniform across all possible t's. Okay? It quantifies over these relations. Okay? So what happens is Dan gave us two implementations. So there was implementation, I'll call them 1, and implementation 2. Okay? And it had a underlying type, I'll call it tau Roman numeral 1 and tau Roman numeral 2. Okay? And then, right, that's the idea. There were two implementations of this counter. And in one case, the counter was implemented, I think, going up. And in this case, it was implemented going down, something like that.
Unary and binary.
Oh, unary and binary. Okay, fine. Unary and binary representation. And then you have a relation between them, which says they represent the same number. One's in unary, the other's in binary, but they're the same number. Okay? So what is happening is, so what we know about the client, because of the theorem, because the client has this type, then it satisfies the theorem. Because it satisfies the theorem, it means that the client is oblivious to fictional notions of equality between the two representations. So here's what I know, okay? If you give me an inc, which is related with the two increments, the source increment and target increment, are related modulo the relation of representing the same underlying number at this type. What does that mean? It means you give me things that represent the same number, they're related, and it will give you things that represent the same number on the output. If you give me two incs, all right, so what I'm saying is, if inc is related at t arrow t, let's say inc Roman numeral 1 to inc Roman numeral 2, modulo the fiction that t is r, where r means same number. In other words, unary and binary are the same number. That's what that relation is. So what the client is saying is, if this is the case, and this is the case, and remember, what does that mean? Okay, it means that given related inputs, I'll give you related outputs. Okay, and if, what do I have? T to nat, so we have val 1 is related at t to nat val 2. Again, these are all modulo the same thing. Okay, what does that mean? Related things, when you compute their value, have to give you the same nat as output. Okay, the same number as output. And finally, if the zeros are related, so if all of that, then client, when instantiated with tau 1 and applied to successively inc 1, dec 1, val 1, and 0, 1, is the same as behavior as client tau 2, inc 2, dec 2, val2 and 0, 2. Period. This is representation independence. The client can't care about the two different representations. It cannot tell the difference, provided the representations are related as specified by their type. If you have related things specified by their type, see, the types are driving everything. The requirement on how Inc1 relates to Inc2 is entirely determined by its type. Same for dec, same for val, same for 0. Modulo the fiction that things of the abstract type are related by this, they represent the same number. Okay? So we can do that. If this is the case, okay, so this is called bisimilarity. If you give me bisimilar implementations, then I give you identical results. And it's all because the client is polymorphic and we have this theorem, the big theorem. Okay, so the big theorem, together with the client being polymorphic, tells us that if you give me related implementations, I will give you the exact same results. That is, the clients are oblivious to the representation of the abstract type. Boom. That's the theorem. Okay? So that's what I wanted to tour you through in this lecture. So that finishes it. Finishes the question.
On the second line of the bisimilarity, should deck 1 be related to deck 2 instead of...
I suppose, I hope I said that. Yeah. Oh, yeah. Sorry. Typical mistake of mine. Okay. Yep. It's a lot to absorb, isn't it? Okay. Yes. It's a lot to absorb. Don't feel bad about that. It's fine. It's all written in the book, a chapter on parametricity. We can talk about it at a work session this afternoon. But this is the thing you need to understand, honestly. Okay, if you can get your way through all of how this works, then you've learned a lot. Okay, so I admit there's a lot of work involved in proving all of this. So, but this is the thing it gives you. There's a payoff for doing all that work, and in a way, this is like one of the shining achievements of programming language theory. And it's all, in my mind, it's all due to Reynolds. Okay, and so I would like to give him credit. But of course, Reynolds, like everyone, built on other ideas. So there's no question about that. But Reynolds really brought out this idea of parametricity, and for decades, people ignored him. Okay, and that's one of the tragedies. Poor John died before he could get the Turing Award, which he richly deserved. And well, that's often the way it goes. People don't get recognized in their lifetime. You have to separate real achievement from recognition. Those are like two different things. So Reynolds would be a good example of that. So he developed essentially all the theory I'm describing here, and I think it's quite a tribute to him personally. But it's really a good example. Like if your fellow students or faculty in your department, more or less say or imply to you, PLs, right? It's all just about parentheses and curly braces and some other bullshit. Okay, it's all just common sense. Well, you see how much common sense this is. See if they can rattle this off. Okay, just say, here's the pen. Would you please prove Reynolds' parametricity theorem for me? Okay, they won't even know what you're talking about. So then you can say, all right, I know where you're coming from. Okay, so it's a pity, but this is like one of the most beautiful and important and powerful ideas in all of computer science. Yet everyone has heard of P and NP, which is totally useless, and nobody has heard of the parametricity theorem, which is completely useful for software development. It's a ridiculous topsy-turvy world. Okay, if they resolve P and NP, it won't make a damn bit of difference to anybody but it's 6 people who care about that piece of combinatorics, and no significance. But this is like practically important every single day, all the time, constantly, every time you run ML. So it's a very, very significant thing. Okay, so I'll finish with that and enjoy bushwhacking your way through all this. It's good for you. Okay, all right, thanks.